Now we're going to consider some vector arithmetic. One operation we can perform is called scalar multiplication. And if we let C represent a real number and A with an arrow over it be the vector, let's say that A has components A1, A2, A3. And by the way, by saying that, what I'm saying is this vector is in the space V3. V3 is the set of three-dimensional vectors. Now, when we talk about like R2 and R3, those look like exponents because really the XY coordinate system is R by R. So they've denoted that R squared, or R2 is how we say it out loud. And then R3, same idea. But with the vectors, it's V sub 3. I don't have an explanation for why that is, but I want you to know what it is when you see it. Back to what we were talking about, for C and A, scalar multiplication is C times A, and it has the effect of multiplying each of the components by C. And so we'd have CA1, CA2, CA3 as the result. Notice the C doesn't have a hat on it. The A does have the arrow on it, and that's how we distinguish a scalar from a vector. Another way to put that is, if I were to write this CA without putting the vector arrow over A, it would be incorrect. Now, because of the relative sizes of the components of CA, the vector CA will point in the same direction as A. It will have a different length depending on what C is. If C is larger than 1, then it will be longer than A. If C is smaller than 1, then it'll be in positive, then it'll be shorter than A. And if C is negative, actually that would affect the direction. To show you what I'm talking about here, here I've drawn a vector A, and I'm letting you know where it is in my mind's eye, terminating above the second quadrant, or the first quadrant over here. And now I've drawn a vector that is twice as long and is in the same direction, and it is the vector 2A. It would have components 2A1, 2A2, 2A3, and it would terminate at a point Q, which is given by the same values, 2A1, 2A2, and 2A3. And I see I've made terrible use of space here, but you get the idea. We could also consider a vector that's half as long, and that vector would be called 1/2 A. So we can see that we are essentially scaling the vector, right? The black vector A here could be twice as long, could be half as long, depending on the scalar multiple, and this is why it's called scalar multiplication. It's scaling the vectors. And the vector negative A would be of the same length as A, but point in exactly the opposite direction here. And what I've done is I've done some things that I think kind of help the eye a little bit. That is, I've given you the x and y coordinates of the trace in the xy plane of A, and then to indicate that negative A is back underneath the third quadrant, I've just given you some marks for, with respect to the x-axis and the y-axis, and then little dots letting you know that it's below the axis. These little right angle things right here, I think just help sell the picture. So those are some things you can do to help your reader see things the way that you intended.